Welcome to the Explainer. Okay, today we are looking at a framework that literally challenges the very building blocks of reality. I mean, we all know the basics, right? Electrons are negative, protons are positive, and neutrons are neutral. It's pretty much the absolute bedrock of physics. But what if that absolute electric charge is actually just a trick of perspective? Let's dive right in.
So, what if positive and negative charges are just an illusion? I know, it sounds completely like science fiction. We measure charge, we literally feel static electricity, we harness it to power our entire cities. How could it possibly be an illusion? Well, a really fascinating theoretical framework has emerged recently, suggesting that the positive or negative labels we just sort of slap onto particles, they aren't absolute intrinsic properties at all. Instead, they might simply be relative assignments, entirely dependent on the frame of reference of the observer.
There is no absolute positive or negative charge. There's only a relative orientation of spin orbital geometry. This core premise was brought forward by physicist and mathematician Dr. Rihan. And to kind of wrap our heads around this, I want you to think of a 3D object, like a cylinder, casting a 2D shadow on a wall. Depending on exactly how you hold that cylinder, the shadow might look like a perfect circle, or, it might look like a long rectangle. The cylinder itself hasn't changed at all, but your perception of its geometry definitely has. Dr. Rihan's theory argues that electric charge works exactly the same way. It is a relativistic, observer-dependent assignment. So, to really grasp how this works, we're going to need to completely dismantle our classical understanding of physics. All right, Section 1, the illusion of charge.
So in classical physics, a particle just is positive or negative, right? No matter how you look at it. But in Rihan's theory, the sign we ascribe to a particle is just a projection. You see, every particle has an intrinsic spin vector. The spin actually defines an orbital plane and a preferred conductive direction. According to the theory, what we actually measure as charge is literally just the projection of that intrinsic spin vector onto the observer's time-like direction. If you change your frame of reference, or if that spin axis rotates, that projection can completely change signs. The absolute crucial point here is that positive and negative are purely relational concepts.
Moving on to Section 2, inside Rihan's atomic model.
Okay, so how does this actually look at the atomic level? Well, in Rihan's atomic model, sometimes called the RAM, every single atom is visualized as this beautifully nested set of concentric Gaussian surfaces. Basically, I want you to picture those classic Russian nesting dolls. If we pop open a hydrogen atom, right at the very center for step 1, we find a 3-quark core that's surrounded by this sort of energy fog. Now we start adding our nesting dolls. Step 2 is the neutronic envelope. Right outside of that, for step 3, we have the protonic envelope, and finally, enclosing the whole shebang in step 4, we have the outermost electronic surface. Notice how the protonic envelope is literally sandwiched right between a neutronic layer and an antineutronic layer. This specific geometry isn't an accident. It is highly intentional and mathematically critical to the whole theory.
And this brings us to a really massive takeaway. Macroscopic matter interacts exclusively through those outermost electronic Gaussian surfaces. Ordinary matter essentially faces the world only through its outer electronic jacket. This outer layer dictates absolutely all of the electromagnetic interactions we ever observe and measure in our daily lives. If two atoms bump into each other, it's their electronic jackets doing the talking. Now, keep that in mind because this specific detail is going to be incredibly important in just a few moments when things get a little mind-bending. But first, we really need to understand the mathematical engine that keeps these Russian nesting dolls from just collapsing into chaos.
Which brings us to Section 3, the unifying ME equation. To make these nested layers actually work, the theory introduces something called a Faraday quarter rotation. Simply put, this is a 90-degree phase shift in the complex electromagnetic field. So the key here is that each one of those nested Gaussian envelopes we just talked about, the neutronic, the protonic, the electronic, is rotated exactly 90 degrees relative to its immediate neighbor. The Faraday operator literally maps one Gaussian layer into a plane that is entirely perpendicular to the one right before it.
And all of this is governed by the ME equation, which stands for Maxwell-Euler equilibrium. This equation is doing some serious heavy lifting here. It takes classical Maxwell dynamics, the standard equations that rule electromagnetism, and it embeds them inside a complex, phase-weighted continuum. It essentially uses Euler phase factors to enforce a global equilibrium. So what does that actually mean for us? Well, it means the theory brilliantly recovers all of classical physics. It doesn't break what we already know works, but by weighting the fluxes and source terms with these phase factors, it simultaneously allows for a much, much richer reality.
It's a statement of local equilibrium and a global conservation law all at the same time.
Let's jump into Section 4. Welcome to orthogonal worlds.
Okay, this is where those 90-degree rotations lead to a truly massive mathematical consequence. I actually want to read this direct quote from Dr. Rihan. Can this world, like neutrons, pass through our world and through us without we feel, without clash, without watching or perception? Since the Faraday operator maps one layer 90 degrees to the next, it begs this absolutely fascinating question. What happens if we apply that exact same quarter rotation, not just to a single atomic layer, but to an entire reference frame? What if an entire world is rotated 90 degrees relative to our own?
The implication of that orthogonal rotation is just incredible. In our reference frame, electrons and protons are charged, and neutrons are neutral. But if you shift 90 degrees into a perpendicular world line, the roles of the particles completely flip. In this orthogonal world, neutrons and antineutrons acquire the projective charge, meaning they act as the charged particles. Meanwhile, our electrons and protons appear completely neutral to them. And remember what we learned earlier, how matter only interacts through its outermost electronic jacket? Because the orthogonal neutrons don't couple to our electronic Gaussian surfaces at all, this entire invisible orthogonal sector of matter could pass right through our world, literally right through your body, without any electromagnetic scattering whatsoever. They wouldn't interact with our matter at all. We wouldn't see it, we wouldn't feel it. Now, I know this sounds like pure science fiction, invisible worlds just passing through us on a Tuesday, but we have to bring this back down to Earth. This isn't just philosophy, it is a mathematically closed theory.
So, Section 5, Testing the Unseen.
So, how do physicists actually search for something invisible? Well, they look for the footprints it leaves behind. The theory predicts very specific experimental signatures we could hunt for right now in a lab. First, anomalous neutronic transmission. Basically, we might detect neutral-looking particles that shouldn't be there but are nonetheless carrying energy or momentum. Second, we can look for the modulation of ionic Gaussian surface philosophies. Remember that global ME balance? The theory states that an excess electron, a negative ion, actually lowers the speed of that outer electronic surface, while a missing electron, a positive ion, raises it to maintain equilibrium. We can actually measure for those precise velocity shifts. And finally, if the 90-degree orthogonality isn't absolutely perfect, there might be tiny phase deviations leaving behind minuscule residual electromagnetic couplings that our highly sensitive instruments could detect. But, of course, as with any groundbreaking theoretical physics, we still have some major hurdles to clear before this becomes accepted textbook science. There are some huge open questions here. For one, if an orthogonal sector does exist, how does it organize itself into atoms, molecules, or macroscopic matter? Does gravity still link our world and the orthogonal world, even if electromagnetism doesn't? Mathematicians also need a much more precise definition of the inner product between two mutually orthogonal sectors. And physicists really need to figure out if this entire framework is compatible with heavily tested principles, like CPT invariance and the strict quantization of charge. Elevating this really beautiful geometric insight into a fully predictive physical theory, yeah, that's still a very active, open research question.
Which kind of leaves us with a pretty provocative thought. If a completely invisible universe, filled with particles we consider neutral, but which act charged in their own dimension, could be passing through you right now, without you even noticing, what else is hiding in the math? The beauty of theoretical physics is that it continually reminds us that the universe is far stranger, far richer, and far more deeply interconnected than our simple human senses could ever perceive on their own. Thank you so much for joining me for this explainer. Keep questioning the basics, keep exploring the math, and I will see you next time.